yeah, not much you can do with that. There's 4 questions, so perhaps it's half an hour each per question.
Yeah, and something I like to do is get my watch out, and when the exam starts, I write down on top of each question when I have to finish that question. So on top of if the exam starts at 1, I'll write down 1:30 on the top of this page, and when 1:30 comes, I am done with that page. Yeah. Be brutal, be severe. Right. Finish whatever you're doing.
You're allowed to do it in 25 minutes too, if you can.
Yeah,
and then have a bit of time at the end.
The idea is that you don't spend all your minutes on one question, because you can spend 2 hours on question 1 and get it perfect, you'll still fail.
I think these people have done exams before, though, haven't they?
That's such a good tip, though. I want to tell them every time. All right, next part. So answer all the questions.
Yes, it's better if the more questions you answer, the more marks you're going to get.
Yeah, wise words. Those ones. Questions of equal value, look, they're all worth a quarter of the marks. Yep. Answer each question in a separate book.
Yeah, this is really important. We have, an unfortunately large pile of, unfortunately large pile of questions sort of mixed between books, and the markers have to go, say, where's this one here? Go and find that one, and it's difficult to make sure everything gets marked properly when they're given out to 4 different markers, and it's all mixed between the booklets. So really do separate them into 4 separate books.
Yeah, it is a bit hilarious though. I actually quite enjoy the kind of comedy of it. It's like, this person wrote everything in question 1, except Anyway, we told them to write each in separate book, and usually in semester 2 they tend to get that right.
MATH1231 students are better at
that particular instruction. This paper may be retained by the candidate.
Yep, you can take it home with you, show your friends. Yep.
And only calculators with the approved sticker can be used.
Yep. Or you don't have to have a sticker on yourself. You do most of the calculations.
Yes, or you can be bold and take no calculator.
Yeah.
Please get your calculator approved before the day of the exam. I have had people come up to me, hours before the exam saying, "Help! I need my calculator approved."
Yeah, that's probably not going to happen.
It's not worth it. Not worth the stress. Do it beforehand. Short table of integrals and the standard normal table are appended to the last pages.
That's right. If you're looking for an integral, look on the last page.
Yeah, and get used to using a table, the standard normal table, because you'll need to be using the standard normal table. Be very familiar with how to use that table before the exam starts.
Yeah. Okay.
All right, question 1. All right, one of mine. There's my answers. Okay. You have a set S. Hopefully it appears here. Show that the set is closed under addition. So hopefully you know how this story goes. When you're proving one of these vector space axioms works for a set, you need to take any 2 elements, well, in this case, you need to take arbitrary elements of the set. You don't know exactly what shape they look like. They could be any elements of the set, so we'll start with that. Let x and y be elements of S. Now, the closure under addition axiom says that if you start with 2 elements of S, you must end in S. So I'm just going to write down here. It doesn't matter what the question is. If you're showing that the set is closed under addition, this is the starting sentence and this is the concluding sentence. And as soon as I see this stuff when I'm reading one of these questions, I know I'm onto a good thing, because they're starting with the right start and they're ending with the right end. And the point is, now I need to look at S to actually get from here to here. So if X and Y are in S, then what do I know? X and Y are elements of R3, and see, x1 plus 2x3 is greater than or equal to 0, and this is the information I have just by virtue of the fact that x and y both belong to S. What I'm actually interested in is that x plus y belongs to S. Then x plus y, what is that equal to? x1 plus y1, x2 plus y2. That's an element of R3. Of course, the addition of two vectors from R3 is an R3. But the important thing is that twice this part plus twice this part should be positive. 2 is equal to x1 plus... Am I still on the screen here?
Yeah,
I'm sorry. Okay, cool. Plus 2x3 plus y1 plus 2y3 is greater than or equal to 0 plus 0, which is equal to 0. So not only is this vector x plus y an element of R3, but twice the first component plus twice the third component. Sorry, you can't see what I'm writing. The first component plus twice the third component is positive, which is the other half of actually belonging to S. Therefore, x plus y is in fact in S, and that's the first part of it done. So that was part A. Part B says to either show that S is a subspace or prove that it's not, and it's not. You always do these questions by proving it's not a subspace by contradiction. You assume it is closed under scalar multiplication, for example, and then show that in fact that's a contradiction. If S were closed under scalar multiplication, say x in S, say lambda x is, and say lambda, I've written it all too close together. If S is closed under scalar multiplication, that means that if x is in S and lambda is just any old real number, then lambda x is also in S. And to prove it by contradiction this is not the case, we'll take a particular value of x from S, we'll take a particular lambda, and show that lambda x is in fact not in S. So let x be equal to 1, 0, 0, which is an element of R3, and let's just verify it satisfies the condition that 1 plus 2 times 0 is equal to 1 is greater than or equal to 0, so x is in S, but negative 1 times x, vector x is equal to negative 1, 0, 0, which is an element of R3, and negative 1 plus 0, 2 times 0 is equal to negative 1, which is not bigger than or equal to 0. Hence, negative x is not in S. This means it is not closed under scalar multiplication. And hence it is not a subspace. Cool. Jonathan, do you want to put your marker's hat on and grab a red pen?
Yeah.
What would you do with this?
Well, I suppose I would probably give you full marks, but I and I like the way you've written what you're doing, so I can actually read it and understand it. But I probably would have actually defined these vectors here so that x1 and x2 and x3 were defined. So I mean, I might have said that where x is equal to x1, x2, x3, y, probably going off the edge here, am I? No, almost. y1, y2, y3.
Mm-hmm.
So if I'd seen that, I would have had a slightly bigger smile on my face. But yeah, I think that's all pretty good. Yep.
Cool, easy. All right, next question. Who's up next?
I think I am.
Oh, sweet.
Yep.
Let me clean this up.
Okay. I can probably just.
I'll wash and you
start down here. Maybe.
Okay. I was gonna. All right. Let's do that.
Oh no, I'll wait.
I'll wash and you dry. How about
Okay.
that?
Okay, so the next question, and blank hand of course. The next question we have is part 2, and we've got a matrix A we're given and a vector B, and it asks, the first part asks if B is in the kernel of A and give reasons. Now this is one of these questions where there's it's sort of designed to see if you actually know what this means, because it's very quick and easy to do if you know what it means. But a lot of students would see kernel of A and just start calculating stuff to figure out the kernel of A and then take it from there. But that's a lot of work. If B is in the kernel of A, it means that A times B, the matrix multiplication there, is 0. So what we want to do here for part A is just calculate this matrix product. So we've got 1, I'll just write the matrix out. 1, 3, 1, 1, 0, 1, 1, minus 1, 2, 5, 1, 3. This is a vector in R4. I didn't do a very good job of drawing the board. You won't have that problem in the exam. So I've multiplied this out. You need to do matrix multiplication. I won't labour the point too much, but it's 1 times 1 plus 0 plus 0 plus minus 1 is 0, and then 1 minus 1. And that is not equal to the 0 vector. So this vector is not in the kernel of the matrix A. If this turned out to be 0, it would have been in the kernel, but it's not. So this is a reason that B, that's B there, B is not in ker A. Okay, so B is not in the kernel of A. The next part was to find a basis for the image of A, and in this question it doesn't actually have the give. Notice the first part had give reasons, so this is my reason. The second part doesn't actually say that, so it probably can be a little bit lighter on an explanation. So what do we want to do to find a basis for the image? Well, the image is the vector space that comes from the span of the columns of A. And so really what we want to do is figure out how many of these columns we need to is the sort of smallest spanning set for the span of these columns. Notice these columns are in R3, so it's certainly not going to be any more than 3 of them if we have a basis, and maybe it's 2 depending on the what the image turns out to be. Okay, so I'm just going to jump straight into some row reductions, which is something I don't really like too much, but I'll maybe explain a little bit. If you wanted to know what is the a basis for the span of these columns, you're really interested to know what's the smallest set that actually spans them. So what you would be solving to find is essentially which ones you can throw away, and maybe you can write this one in terms of these and this one in terms of these, and then you can throw it away when you're writing a basis. So in doing that, you'd probably have an augmented matrix with 1 extra column, but we don't need that here because that, we could do that, but we're not going to actually need that information. So I'm just going to row reduce this matrix, and let's see what we get. So I'd like to put it in echelon form. So I'm going to do row 3 goes to row 3 minus 2 row 1. That's 1, 3, 1, 1. And then 0, 1, 1, minus 1. Haven't changed anything there. And 0, I got this wrong before, minus 1. So this is 5 minus 6, yes. Minus 1, 1. And actually, at this point, you can see this last row is just a multiple of that one. So I know what's going to happen, but I suppose I feel like I should explain it properly. So the next row operation to put more zeros here is actually going to give us a whole row of zeros. Okay, so now in this reduced form, if this was an augmented matrix and we were trying to find out, which vectors we can get in the image, or which ones of these we can write in terms of other ones, we'd be solving a system of equations here, and it's really these pivot elements that tell you which vectors in the original set are enough to write the other ones. And I suppose that there's a sort of standard technique that says that you can take this one here tells you need that vector, and this one tells you need that vector. Well, actually, you don't need them. There are other possible combinations as well, but this is one that definitely works. So a basis for the image of A is those two vectors there that correspond to the leading columns. Okay. All right. What do you reckon? Do you want to get some red pen? Yeah. I don't like my explanation actually, but I've gone for the fast, get the marks approach here, which is very much against my philosophy.
But I think that's appropriate in when you have half an hour to do 6 questions.
Yeah.
Is B in the kernel? Give reasons. I buy that as a kernel, as a reason. It doesn't multiply to 0, so it's not in the kernel. And find a basis. Look, you don't really have to do any more than that. I think you could. No, look. Strictly speaking, I would say this is a perfect answer for an exam. Wouldn't teach it this way in a lecture, but
and if it had said, you know, explain what you're doing, give reasons or something like that, maybe you might have a little bit more. I don't consider this to be a reason. I consider this to be the working that maybe gets you the answer.
Yeah, there's some things that we could do just to sanity check. There's 2 leading columns here, which means the image is actually a 2-dimensional beast, and Jonathan's got 2 vectors here, so at least I could do a quick sanity check to make sure this sounds sensible.
Actually, also some little sanity check here is that the kernel is at least 1-dimensional.
Yes,
because we've got something in the kernel, and the rank nullity
how do you know
theorem.
you've got something? Well, but just by the rank nullity, by the shape of the matrix,
Sorry.
you don't know you have something in the kernel.
Yeah.
You could have 3.
Yes.
Well,
actually,
of course, it's a
right.
It's 4
okay, so for those students who had taken the long approach here and found the kernel, they would have found something 2-dimensional, and then that would have worked, wouldn't it? Yeah, that would have made sense. Okay,
we move on. Josh, you up?
Henry's got it in his hand.
Okay. We're moving from vectors all the way to the probability end of the course. So you can see here, we're looking at a question about a normal distribution. So we're told that we have the height of the male students in university distributed normal. So it's distributed like a normal distribution with a certain mean and a certain variance. So you do need to translate what is written in the question into some sort of mathematics you can use. So first things first, I want to define our random variable. So I just want to say let, well, its heights, so h be the heights of male uni students. Then according to the question, so if you read the question, it says that the heights, so h is a random variable, and it's distributed like a normal with a certain mean and a certain variance, where, well, if you look at the question, the mean is 172 centimeters, and the variance, in this case the standard deviation, so sigma, is 5 centimeters. So it has this mean and this standard deviation. So what the question is asking us to do is we want to interrogate this distribution. We want to answer a particular question about this. And the question we want to answer is, what is the probability that the heights, so you're randomly choosing a height, what is the probability you get a height which is greater than or equal to 180? Now this is just a normal random variable, but unfortunately when I look at the back of the book, they didn't give me a normal with this mean and this variance. All I have is a standard normal. So I need to somehow turn this into a question about a standard normal. So the way you can do that is we'll just take this and shift it so it's now centered around 172 and scale it so that the standard deviation becomes 1. So we're looking at the probability, so I'm going to shift this down by the mean, I'm going to scale it down by the standard deviation, do the same thing to 180, in this case I'll use the actual number. And I'm asking this question, I'm asking what is the probability that this quantity here is greater than or equal to that? So, well, this is the same as the probability that a standard normal, now I'll get back to this, I can't just really write z, because that doesn't make any sense without any definition. But going for z greater than, well, 180 minus 172 is 8, so we get 8 over 5, and 8 over 5 is 16 over 10, so it's greater than or equal to 1.6. Just so I don't, no, if this is wrong, someone will probably correct me. So we're looking at the probability that we're 1.6 standard deviations up. And I should explain, here z is a random variable distributed like a normal 0, 1. So now I've defined what I mean when I say z. So this is nice, this is almost a quantity I could look up on the table, but not quite. There's two ways to do this. This is a very symmetric distribution, so I could exploit that property, but what I will do is I'll rewrite it as the complement probability. So 1 minus the probability that z is less than 1.6. And I can look that up on the table now, because that is what the table says. Actually, for a continuous random variable, less than or equal to and less than is the same for a continuous one. So I'm getting 1 minus 0.9452. Okay. Now if I do that subtraction, I get 0.0548, and I can verify that because there's another way to do this question. Yes. Right. So that is the number I was looking for. I have a 0.0548, but that's not quite answering the question. I need to interpret what I just did. So in this last little bit of board space, in the book this would be nicely laid out, but on the board it's a little bit messy. So hence, the probability we were looking for is, well, 5.48%. So it's a little bit unlikely that we'd find someone quite that tall. Any comments on this?
Are you taller than 180 centimeters?
I am unlikely, that's true.
But you're also not a student.
Yes, that's true. I don't think I changed. I didn't suddenly shoot up after I graduated.
Cool. The only thing I look, it's just a very minor point, but the only thing I would suggest about here is that this is, the table is a list of approximations, so this is approximately equal to that.
Oh, I don't think that's true.
Really?
Well, I mean, it's finite accuracy, but this number is exact, 1.6.
Mm.
So,
but the probability that z is greater than or equal to 1.6
well,
is, I mean, this is truncated. This is approximated
yeah, okay,
4 decimal
I
places.
suppose, yes.
So this is perfect, but this is, you know, subjected to the physical limitations of our
table. Yes,
table.
we didn't want to give you an infinite length table. Okay.
It's too expensive. All right, cool. My turn. Oh, unless Jonathan, you wanted to say something here?
Yeah, except I thought it was my turn.
Oh, it's your turn. Oh,
Yeah.
excuse me. Sorry.
You can clean the board if you like. Yeah, I don't mind that. Where's the wet? Oh, you got the wet one? I'll follow behind you.
Mm-hmm.
That doesn't seem. Drag things out of order.
Black pen. Right, so I've got some integrals to do. So let's just get straight into them. So the first one is a pretty standard trig integral. So we're integrating. It's just an indefinite integral, no limits. Cos cubed x times sine to the fourth x dx. Okay, so this kind of an integral is a pretty standard ones that you need to sort of recognise straight away, know what to do. And because sine and cosine are, roughly speaking, each other's derivatives, this usually works by just taking off, well, if there's an odd power of either sine or cosine, then you can take off one of those and then use a sort of substitution. So anyway, let's just see how it works. So because this is an odd power, cos cubed, I'm going to just take one cos off on its own and leave a cos squared. And now we've got, so cos squared x sine to the fourth x times cos x dx. And this cos here is essentially the derivative of sine. That's why I think I'm on the right track. And even powers of cos we can convert into sines without any square roots. So cos squared, everyone's favourite trig formula says that's 1 minus sine squared. So this is really sine to the fourth x minus sine to the sixth. Brackets there, and I could use a substitution now. Maybe u equals sine x, but I think I can just do this one in my head. This is going to be sine to the fourth is going to come from sine to the fifth, 1 over 5, and because we've got cos x here, so this, if I differentiate this 1/5 sine to the fifth x, I'm going to get 1/5 times 5 is 1. Sine to the fourth x times the derivative of sine, which is cos, which is that. So this is right. So you can use a substitution there if you want, but I think that's probably overkill in this situation. And that's the answer. Plus c on the end. Yes. Okay. So the other one, part B, is a rational function. So maybe I won't start with the integral itself. I'll start by converting this rational function into a form that we can integrate using partial fractions. And the first thing to notice here is that the numerator has a lower degree than the denominator, so we can just jump straight into finding partial fractions. We don't have to divide first. So we've got 3x squared plus 11x plus 12 over x plus 1 times x plus 3 squared, sorry. Okay, we'd like to rewrite this using partial fractions, and so you need to know what to do with different forms you might have down here. In the denominator, you're only ever going to have linear factors or quadratic factors, or after factorising perhaps. This is slightly complicated by the fact that this is a linear factor squared. So you need to make sure you know what to do with each of these things. The first one, we just try a term of the form constant over this factor, and then we have another constant over x plus 3 and another constant over x plus 3 squared. If it was a quadratic factor that wasn't reducible, then we would do something like bx plus c over that quadratic factor. And you could do that in this case as well, but this form is chosen because it's easier to integrate. Okay, so this is the one you should use. All right, now there are tricks that you can use now to actually work out a, b, and c pretty quickly, but I'm not that smart, so I'm just going to multiply across by the denominator and take it from there. So multiplying by x plus 1 times x plus 3 squared, I'm going to get a times x plus 3 squared, b times x plus 1, x plus 3. Am I going to go off the edge here? You can tell me in a minute. X plus 1. C times x plus 1.
You're in.
Okay, good. So now we just have to figure out what a, b, and c are, and there's lots and lots of ways you can do this. The simplest, of course, is just to pick some values of x, which make lots of things disappear. And of course, choosing x equals minus 1 will kill off that term and immediately tell us what a is. So let's just do that. So on the left-hand side, if we have x equals minus 1, then we get 9 minus 11. Is that right? Yes. Oh, hang on. Not 9. 3. 3 minus 11 plus 12. And on the right, then we get a times a equals minus 1, so that's 2 squared. Times 4 plus 0 plus 0. And that immediately tells us what a should be. So 4a is equal to, what's this here? This is 1 plus 3 is 4. 4a equals 4. So a equals 1. And x equals minus 3 is another good choice. That'll kill off some other terms. So that gives us 27 minus 33 plus 12. That's just substituting minus 3 into there. And that's going to give us, that's going to be 0. That one's 0. And that one is minus 2. And that will then tell us what c is. So c is minus 3, I think. Just, yeah, c is minus 3. Yep. Okay, so we've got one more to determine. There's lots of ways you can do this. I reckon probably the best way is just pick off the coefficient of x squared on both sides. This is a quadratic on the left with 3 in front of x squared, and on the right there's an x squared here, so it's a, and there's an x squared here plus b. So a plus b is 3. So this is coefficient of x squared is on the left 3 and on the right a plus b. And since we already know what a is, which is 1, b must be 2. Okay, so now we know how to rewrite this in this nice simple form, which we can integrate. And I think I've even got room down here.
Maybe do it over.
You reckon over here? Yep. Yeah. Okay. I'll do it over here. So yeah, there's no prizes for using the smallest amount of paper in the exam. Okay. So what we want here is the integral of 3x squared plus 11x plus 12 over x plus 1 x plus 3 squared dx is equal to the integral 1 over x plus 2 over x plus 3 minus 3 over x plus 3 squared dx. I think that's right. So the 1 is the a, the 2 is the b, and the minus 3 is the c. Yes. Okay, so this now integrates to the natural log, the absolute value of x plus 1, plus 2 times the natural log of the absolute value of x plus 3, minus 3 over x plus 3 plus constant. Okay, I think I'm done. Yeah.
So two questions. Do you have strong feelings on the use of absolute values here?
This is certainly true for all values of x except when this turns into 0. If not, then the natural log of a negative number doesn't make sense unless you believe in complex numbers. You can make sense of it then, but this course is about calculus of real variables, so I very much prefer to see these absolute values in here because it's actually true for a bigger range of x values here.
Cool. So I think that's something that's worth pointing out, the use of the absolute values here. I personally don't have strong feelings about it, but I know some people do, so I just advise to go all out formal and put your absolute values there.
This is, otherwise, certainly it's true if you want to put minus x minus 1 when this is a negative number. That's true, but that's a bit complicated. That's what the absolute value does for you.
I don't think we need to go into that. Absolute values.
Absolute values, yeah.
Cool. All right, my turn. Oh, and I like the nifty use of finding the coefficient of x squared here. They're really, that was slick. So I just thought I'd point that out. Alrighty. What have I got? Okay. So, part A. Solve. Solve this thing. I advise you to solve this equation. I advise you to just solve this in the fastest possible way. So you can jump straight into the characteristic equation. So since and if you encounter a quadratic, you can just use the quadratic formula to solve it. You don't, in this case, you can't factorize it. You do in fact need to use the quadratic formula. So 4 plus or minus 2 plus or minus 2i. And so the solutions. Say their y of t equals a e to the 2 plus 2i t plus b e to the, that's a minus 2 minus 2i t. And we prefer, when you've got something like this, we prefer you to write it in terms of sines and causes. So I'll take the e to the 2 out the front. This is e to the negative 2t, sorry. Let's call it c cos 2t plus d sine. Where the c and the d are potentially complex numbers, and instead of writing e to the 2it plus a e to the 2it plus b e to the negative 2it, we're writing them as causes and sines. For part B, it just asks you to guess, or it asks you what form of the solution should you try if you've got 8. This differential equation equals 8 sine 2x, and you try for your particular solution. You don't actually have to sub it in. You try y p t can be equal to e
Daniel, is
Yes.
the correct complex number? It's root
Where?
minus 4
Root minus 4.
would give you a plus minus 2i. Divided by 2 is plus or minus I.
4 square root 4 is 2. Divided by 2. What have I done? Should it just be I?
I think it should just be I.
I agree. It should just be I. Thank you.
You can thank the audience.
Thank you, audience. I. There we go. No, I still have to guess that with the 2's. There. Excellent. There.
Yep.
Any other suggestions?
Yeah, I mean, I probably would just jump straight to here, but it's nice, you know, to remember that it's not just magic. It does actually
Yeah.
come from what we know about complex numbers. Yeah.
Cool.
Was that that question?
That was it. I had a short
Okay,
one.
I think Josh is up next.
So we're looking at this power series. So we want to determine the open interval of convergence for this power series. Now it is quite a complicated looking formula, but we can handle this. So first things first, I want to define some notation. So when you're coming to power series, the open interval of convergence comes from using the ratio test. So first things first, let's define the terms in this series. So let's give them a name just to make it easier to talk about them. So I'm going to let AK be this term, which is, well actually I'll call it AN to be consistent with that notation. So it is 2 to the n over n squared plus, no, minus n plus 1, 3 to the n, multiplying onto x minus 3 to the n. So we're trying to sum up these terms, and we want to know when this sum converges. So the basic test you use for the power series is the ratio test. So let's consider what the ratio test would tell us. So to do the ratio test, I need to look at the limit as n goes to infinity of a n plus 1 over a n. I'm taking absolute values just so there's no minus signs to think about. And well, this is again not pretty because there's so many terms. But we're going to be looking at the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 squared minus n plus 1 plus 1, 3 to the n plus 1, and still space, yes, x minus 3 to the n plus 1, all of that divided by the same term but with an n instead, which is a bit easy to write, 2 to the n over n squared minus n plus 1, 3 to the n, x minus 3 to the n. It's a bit off camera, but that's fine. So we want to look at this quantity here. Thankfully this does simplify fairly significantly before we take the limit. So there's a 2 to the n plus 1 on the top and a 2 to the n on the bottom. So that becomes a 2 when I cancel out 2 to the n. On the bottom of this term there's a 3 to the n plus 1. This is on, well, this is in the bottom of the bottom, so it flips on top. So when I cancel it out I get a 2 over 3. So you might have to think about dealing with this fraction, but you will get a 2 over 3 from those two terms. This next one's not pretty. No, in fact, this is the ugliest part of it. We end up with an, let's actually do this properly, n squared. I'll get a 2n and a minus n give me an n. I'll get a plus 1 minus 1 plus 1, which is going to be plus 1. But n squared minus n plus 1. And these cancel out nicely just to give me x minus 3. So the only thing that's varying as n gets large is this term here. Now, I could do this properly, but I'm just going to say that I can see that the dominant term on top is n squared, the dominant term on the bottom is n squared. So as n gets very, very large, this tends to n squared on n, and that tends to 1. You can do it more formally, but I think you should know that this ratio here will tend to 1 when n gets very large. So we get, when n is very large, this is just 2/3 the absolute value of x minus 3. So that's what's going to happen to that ratio for large values of n as n gets large. All right. Now, what the ratio test allows us to do is use this to define a range of x's where we know convergence is certainly happening. So let's just state what the ratio test promises. It promises this will converge when this ratio, so this limiting quantity here, is less than 1. When I get 2/3 x minus 1, x minus 3 is less than 1. I don't know what's happening when this thing is equal to 1. The ratio test doesn't know what happens there, but we don't really mind for this one. We just want this inequality here. So what does that imply? Well, you can write this as x minus 3, the absolute value of x minus 3 is less than 3/2, so 3 over 2, which is 1.5. And that's the same as having, well, that's the same as having x minus 3 between minus 3 on 2 and 3 on 2. So minus 1.5 up to 1.5. And if we just shift everything along by 3, you'll find that this means x is between 3 over 2, because 3 is 6/2, so 3 wholes is the same as 6/2. And shift this up 6/2, I get 9/2. So I get x is between 1.5 and 4.5. All right, am I still on the screen? Yes. So that allows me to draw my conclusion that hence the open interval of convergence is, well, it's the interval from 3 over 2 to 9 over 2. So x's in this range will definitely give us convergence. Now it does say open, so we're not worrying about the endpoints for this question. We're just looking at the open interval.
Cool.
So comments?
Is beautiful. I have a general comment. We should pick this up because otherwise we'll be here till 6 o'clock.
Yeah,
So let's move quickly through the next couple of questions.
I think I'm up next.
Let's see. It's a sequence question.
Okay, so maybe I'll just start down low. So this
Dry?
is
Is it dry?
over here. Actually, it's not dry.
There's the
Oh,
thing.
Here it is. Need to get a big fan.
Sorry?
Need to get a big fan.
Yes.
Maybe I'll start up here now. Okay, so we want to decide whether a particular sequence converges or diverges, and if it converges, we want to know the limit. So this one here is I guess it involves a fairly standard trick that crops up in a few different incarnations in a similar way. Okay, so we've got some expression like this. The first thing that comes to mind, basically because I've seen this kind of thing lots of times before, is that I perhaps want to do a sort of trick that's a bit like rationalization. I guess it's unrationalization in this case. Multiply by a fraction with the numerator. Definitely not dry enough, is it? Numerator and denominator chosen to sort of undo those square roots. Can you read that on the screen? Yeah, sort of. Okay, so having done that, just multiply it out, and of course the top line is a difference of two squares, and so that becomes n plus root n minus n divided by, well, there's only one thing on the bottom, and the n's cancel. I can do that double quick time, like so. And now I want to try to perhaps put this in a form where the limit is obvious, and I'm going to divide top and bottom by the square root of n. And so this is going to be a 1 on the top, and on the bottom I take a square root of n inside these square roots, and I'm going to get a 1 plus 1 on root n plus 1. And of course what happens as n goes to infinity here, that goes to 0, and then all the rules about limits with compositions of functions and the algebra of limits tells us this goes to 1 over, maybe the square, I'll do this in a little bit of detail, 1 over the square root of 1 plus 0 plus 1, which of course is just a half as n goes to infinity. Okay, so there's our limit. I found our limit. If I found a limit, it means it converges. So this converges. Now part B is pretty much straight away, because what this part B is summing up all the terms in this sequence. And the terms in this sequence have a limit of a half, and so eventually you're summing up a whole lot of infinite number of halves, basically. So it cannot converge, and there's a special name for that. It's the Nth Term Test. So by part A and the Nth Term Test, the series diverges. We're just summing up these terms, and the terms aren't going to 0. I think I'll leave it at that.
Good.
Running out of time.
Yeah, Josh, you up?
Right, so it's another convergence question. Or, yeah. Well, actually, this is about series, sorry. So it's more to do with the second half. So we have these two series, and we'd like to determine whether they converge or diverge using an appropriate test. Okay, so the first one, well, the terms look like n squared over 2 to the n. So my first instinct usually for these series is to try the ratio test, because it is a very powerful test, but it sometimes fails. And for this one I can see, actually, I think it's going to work. So for part A, again I'll use the same notation, an equal n squared over 2 to the n, and the limit, as n tends to infinity, of, well, these are positive terms, so I don't need absolute values, of a n plus 1 over a n, which is the limit as n tends to infinity of n plus 1 squared over 2 to the n plus 1, and 1 over n becomes 2 to the n over n squared, so just flipping the fraction over immediately. Well, we can rearrange this. The 2's are quite nice because they cancel out to give us a 1 over 2, and the others I can write by dividing by n squared as 1 plus 1 over n squared. Well, that's it, the bottom becomes 1. So I'm looking at the limit of this. And this, well, this tends to 1 squared, which is 1, so this limit is a half. I'm going to call this r. So since this quantity I just calculated, since r, well, be careful, since r is less than 1, the series converges by the ratio test. So this first one was quite easy. It's just the ratio test again. Part B, well, you can try the ratio test, but if you do try the ratio test, you're going to find that these terms, the ratio of these terms tend to 1. The ratio test just says, I don't know. So we need to do something else. Now, if you're looking at that series, you may notice something nice, that 1 over k, which is in that series, we know that, well, if this were a continuous thing, 1 over k is the derivative of log k with respect to k. So we have the derivative of log sitting there. So, consider the function f of x, which is 1 over x log x squared. Well, this thing I can actually integrate quite easily by substitution. So we have the terms. Right. So I'm going to do this quickly. That since, well, this is a continuously decreasing function, so since if I were to look at the integral instead, so instead look at the integral from 0 to infinity, 1 over x log x squared dx, if I integrate that, well, I'm going to do it via inspection. It looks like 1 over log x, and I take the derivative of 1 over log x. I almost get that, but I need a minus sign to really make it work. And just double check that, so it becomes squared minus, yeah, I think that's correct. From x equals 3, and as x tends to infinity. So this is an improper integral, but I'm more concerned about what's happening for large x. So for large x at the upper limit, we get that 1 over log x tends to 0, which is nice. So we're just going to get 0 minus 1 on log 3, or in other words, log 3. So this integral converges. This allows me to apply the integral test. So since the integral 3 to infinity 1 over x log x squared.
Just be 1 on log 3, Josh?
Yes, that's correct. I'm more interested in the fact that it is just a number. It is convergent. What's more important, I think, is that this integral does converge, although it is nice to get things right. So since this converges, the integral test says that the series converges to, I'll just write that out. So yes, they're both convergent. They're both convergent series, but for very different reasons. Right.
Perfect. Let's move it along. So we have in this question a rectangle, and you don't get told what the x kind of initial points are. Really, this is a question about you have some rectangle with a particular area. There's an x value and a y value, and the x value increases and the y value decreases. And what is the percentage change in the area of that rectangle? And you have to use the total differential approximation. So I'm going to let cloth. Thank you. Just for my own personal reference, I'm going to let x0 and y0 the kind of current or shall I say original? Original's probably better. Values of x and y. Then, what does the total differential approximation tell? Well, first of all, then initially the area of my rectangle is a0, which is just x0 times y0, and what I'm interested in is what is the new area once x increases and y decreases. By the total differential approximation, I have a minus a0 is equal to dA dx, the derivative of a evaluated at x0, y0, times the change in x, which I'll just write out as x minus x0, y minus y0. And this thing here, derivative of a with respect to x is just y, evaluated at x0, y0 is just y0. X is increasing. X is increasing, which means that x is 1.05 times x0, so x is increasing, it's 5% bigger, minus x0. And similarly over here, dA dy is just x, evaluated at this point is x0, and y is decreasing, so this is 0.94 y0 minus y0, which I can evaluate as 0.05 x0 y0 minus 0.06, which is negative 0.01 a0. So the difference between a and a0 is just negative 0.1 a0, and the percentage decrease or percentage increase is negative. Which you might expect because the x value is getting bigger, but the y value is getting smaller by 1 y. So you actually would expect to be a decrease in the area.
So I guess the only thing I would write differently, maybe Jonathan will disagree, I would write approximately here, because this is an approximation.
Fair call.
So
Absolutely.
I think the only thing I would do slightly differently, say this is approximately that. So our approximate decrease is this. That's
Nice.
I
Very
think that's
good.
fine.
I agree with that. Let's move on.
You go. I take the cloth?
Yep.
Alright, so for this next question, we have a map. So we have a function which goes from R2 to R3. And firstly, we need to prove that this is not just any sort of function, it's actually a linear one. It's what we call a linear map. So the linearity comes from two conditions. You have the addition condition and the scalar multiplication condition. So we do need to do a little bit of setup for the first part. So first things first, I want to show if I take two vectors, sum them together, that they give the image that's the same sort of structure. So let's let x, let's let x and y be from, I'll take them to be the vectors called x and y be from R2. And to make Jonathan happy, I'm going to say where x is the vector x1, x2, and y, this is a big conflict, and y1, y2. So the components of x are x1, x2, the components of y are y1 and y2. Okay, so first things first, let's look at t of x plus y. Well, what does x plus y means? It means the vector whose components are x1 plus y1, x2 plus y2. So according to the definition of the map here, we're going to take the two components, sum them together. So to apply t to this vector, take the first component, add it to the second component. So that's the get x1 plus y1 plus x2 plus y2. The next component will be twice the first component. So I have to take twice x1 plus y1, so twice the first component. And the last part is minus the second component, so minus this, minus x2 plus y2. So that's not so bad, and I want to really split this into the two different initial vectors, see what's happening. So I can split this all up into x1 plus x2 twice x1 and minus x2 plus, well now the other leftover stuff, y1 plus y2 twice y1 minus y2. Alright, so if I look at this, this is actually the same that I would get from applying the map t to just x by itself. So this is just t applied to x. If you look at it, that's exactly what that quantity is. And the other quantity is exactly t applied to y. So if I take two arbitrary initial vectors and I apply the map to their sum, it is the sum, you sort of sum together each individually. So that's what we want to see. We want to see that hence t satisfies the addition condition. So this is the phrase you'll want to remember. It's the addition condition. Alright, so the other thing we want to do is show that this map satisfies the scalar multiplication condition. So I'm going to do the same thing. So let's take a scalar, let's call it lambda, from our field, which will be the reals. So it's another thing I'm defining. So now let lambda be a real number. Then let's look at t applied to scalar. So I'm taking that vector x, applying lambda, which is say apply the map to lambda x1, lambda x2. And again, we know what the map does. It says to get your first component, add together these two. The second component is twice the first component and minus the second component. And what's nice here is everything has a factor of lambda. So it's lambda times x1 plus x2, lambda times 2x1, and lambda times minus x2. And if you look at that, that is just lambda times x. So hence, t satisfies the so-called scalar multiplication condition. So that's what I want. That allows me to conclude that hence T is linear. So it's linear, it has the addition condition and the scalar multiplication condition. Alright, so that's part A. Part A is actually a bit of work because there's a lot of description. Part B is actually not as hard as it first looks. So for part B we want the nullity. I want to know what the dimension of the kernel of this linear map is. So I'm interested in the kernel of this linear map. So just note the following observation, that if x is in the kernel of T, then, well, that means that T of x is equal to the zero vector. And it's not just any zero vector, it is the zero vector R3. And in terms of the notation in the question, we get that x plus y, 2x minus y equals 0, 0, 0. And if you look at this, well, you get two conditions, that 2x and minus y, sorry, you get that 2x is equal to 0, minus y is equal to 0, and that does imply that the x and y both have to be 0. So anything in the kernel has to be the 0 vector. So i.e. the kernel of T is actually just the set containing nothing but the 0 vector. Therefore, the nullity of T, which by definition is the dimension of the kernel of T, is 0. Because this is one point. If you only have one point in there, it's a zero-dimensional object. So that's the nullity of T, because there's only one thing in there, only the 0 vector. Any comments, or?
I think my comment is we need to speed up.
Yep.
So I'm just going to draw the table down here so I can refer to it later. Okay. So you have this discrete random variable with these probabilities. The first question is to, of course, find C. So part A, since all these probabilities must sum to 1, you can figure out what C is. So since 1 is equal to 0.0, that tells you that 1 minus 0.53 is equal to C, which is 0.47, which is equal to 0.53. So just summing all this stuff up makes you realize that this must be that. The question then asks you to find the expected value and variance, and I'm just going to bang out with the formula for expected value and variance of these things is equal to the sum from k is equal to 0 to 3 times k, p x equals k which is equal to 2.22. And finally, C. Now, the formula for the variance of x, which I prefer that you use, is one that makes the calculation very easy. It's the expected value of x squared minus the expected value of x squared. Of course, when I say those two things, they mean they sound the same, but the squared is in different places. So this one is just expected value of x squared minus 2.22 squared. I just need to figure out what this is, and that's where I come back to the table. I add an extra row on the table for k squared. 0, 1, 4, 9. Because expected value of x squared is going to be equal to the sum from k equals 0 to 3 of k squared times probability that x is equal to k, which is just going to be that times that plus that times that plus that times that plus that times that. And if you'll permit me, I'll just write that out as 5.38. Hence the variance is equal to next question.
Yep.
Sorry, it was a bit terse, but I'm trying to get this done as quickly as possible.
I'll grab that pen. Well, the next question is going to be quick. Looks like a complicated one, but we have how many polynomials are there? 5. 5 polynomials in P3, which is a space of polynomials of degree 3 or less. So cubics and lower degree polynomials are in there. If you're going to write down a cubic, you need 4 coefficients, one for the x cubed, the x squared, the x, and the constant. So this is a 4-dimensional vector space. Okay, so I'll just make a note of the fact that the dimension of P3 is 4. The dimension is the size of the number of vectors in the smallest possible spanning set. So that basically gives us the answers to the parts A and B. We've got a set of 3 vectors, and we're asked to say whether this could be a basis for P3. Well, if the dimension of P3 is 4, a basis must have 4 elements. The question says explain your answer, so we better write down something. A basis of P3 must have 4 elements. Because dim P3 equals 4. Hence, the given set cannot be a basis. It's only got 3. Okay. And there's a similar argument for part B. Could the set of 5 vectors be linearly independent? Well, a basis is the also the sort of the largest linearly independent set you can have in a vector space, and that's got 4. This is 5. So there are 5 vectors in a 4-dimensional vector space cannot be linearly independent. Since the number of elements, I'm just going to say is 5. That's the number of elements in the set, which is greater than the dimension of P3. The set P1, P2, P3, P4, P5 cannot be linearly independent. Actually, the question asked to say true or false. Which of the following statements are true and which are false? It's probably a good idea to actually write that in, I would say. So the first one is definitely false. And the second one is also false. Okay, I think I'm done.
Nice. Sure up.
Alright, so now on to question 3. So third booklet, just replace the board with a new one. So we have a 2 by 2 matrix, and we want to work out its eigenvectors and eigenvalues. Which really means work out the eigenvalues and then use that to find the eigenvectors. Black pen or something.
Oh, both here.
Alright, so first things first, we need the characteristic equation for this. The characteristic equation is the determinant of a minus lambda I equals 0. So that's what we want to have hold. So we're looking at determinant of 4 minus lambda minus 6, 1 and minus 1 minus lambda, which is 4 minus lambda times minus 1 minus lambda. And this is minus 6 times 1, but there's a minus sign from this, so I get a plus 6. And that will be lambda squared. Well, I get a minus 4 plus 1, so I get a minus 3 lambda. And the 4 times minus 1 gives, 4 times minus 1 gives you a minus 4. I have this 6, so 6 minus 4 is 2 plus 2. And, well, you can solve this, but if you look at it, you might realize it is actually just lambda minus 1 times lambda minus 2. And I want that to equal 0. So hence, the eigenvalues, so each of these gives me an eigenvalue, and they each have multiplicity 1, so they'll each have their own eigenvector. The eigenvalues are lambda equals 1 and 2. Those are the solutions. So I need now the eigenvectors. Lambda equals 1. Well, let's just consider the following equation. So as an augmented matrix, I would have 4 minus 1 is 3, minus 6, 1 is 1, and minus 1 minus 1 is minus 2. A quick sanity check tells me that these two really do represent the same equation. I can't have two independent equations. So I'm not going to do the row reduction here because this will have a one. This only will have one solution up to scalar multiple. So I'm just going to pull out that this gives eigenvector, the corresponding eigenvector, call it B1, which is equal to, alright, so I need to balance this equation. A 2 here and a 1 here would work. Same with the second one. So 2 and a 1. And any non-zero multiple of this would all work, but this one's a good one. So any non-zero multiple is also fine. If lambda equals
Can I do number 2? Can I do that one?
That's fine, sure.
Because I do the same thing but in a slightly different way. So what Josh is doing here is pulling out a solution of this, and I mean you could get this from row reduction if you wanted to, but an easier thing to do is just to look at this and extract a solution. So I do the same thing, but I set it up slightly differently. When lambda equals 2, you get the what you're really doing is find the solve. Let's see. To a minus 2i, which is the matrix equals 0. So that thing, I'm just jumping in here, times a vector x is equal to the 0 vector. So this is what you're trying to do. You're trying to find a solution to this. And that solution will be your eigenvector. Now this matrix here, a minus 2i, so a minus 2i is just the 2, negative 6, 1, minus 3. So that n times x1, x2 is supposed to be equal to 0, 0. And all you have to do is find out what x1 and x2 should be. If I let that be 3 and that be 1, then I get 6 minus 6 and 3 minus 3. So I could rub those out and say 3, 1. Since that is equal to that, then 3, 1 is an eigenvector.
You want to be careful though that you don't have a two-dimensional eigenspace.
Yes, that's the thing you need to be very careful of. If you have this only works because you have a one-dimensional eigenspace, and that means that anything I get from this space is the only eigenvector. We know it's one-dimensional because we get distinct roots here. So if you have distinct roots, do it the trick way. Otherwise, you'll need to reduce this thing. Cool. Sorry, Josh.
All right.
There you go.
All right, so we have our eigenvectors and eigenvalues. So the next part of the question, it says write down an invertible matrix. I think this question really should say hence write down an invertible matrix, because we're going to use the information we just got. Now, I always find myself getting a little bit confused about this. So I'm going to do what I always do. I'm going to take these eigenvectors and put them in a matrix and say that, so put them in the matrix, which I'm calling M at the moment, and they are the vectors 2, 1 and 3, 1. So unfortunately, just the way my brain works, I always find it easier to think about A times M. So the matrix times the eigenvectors, maybe put the inverse before, will be a diagonal matrix. And specifically, it will be the diagonal matrix of the eigenvalues. So the eigenvalue of the first one is 1, so I get eigenvalue 1. The eigenvalue of the second one is 2, so I get that. And this is actually, if you rearrange this statement by multiplying on the left and multiplying on the right, you get A is equal to M D M inverse, which is exactly what we wanted. So I always find it easier to remember that M comes here. It's A multiplied by eigenvectors. And that's the answer to the question. So that's the M we want, that's the D we want. Cool.
Okay, so my question is to prove a set is linearly independent and then write the last vector as a linear combination of the other two. So seeing as I've read ahead to what part B asked me to do, I'm just going to say solve. This is kind of part A and B together. Solve lambda 1 times the first vector, 1, 1, 2, plus lambda 2 times the second vector. Equals and of course the way you solve a system of equations like this is with an augmented matrix. And you do row operations. We actually want to extract lambda 1 and lambda 2, so we'll need to go all the way to reduced Row-Echelon form. I'll do, and I'll sneak in a R2 is negative R2. And because I want reduced Row-Echelon form, I'll go the reason why I love reduced row echelon form, and the reason why you should love it as well, is because it allows you to just unpack completely the coefficients. From this row here, it tells you that lambda 1 plus nothing is equal to 5. So this tells you that lambda 1 is equal to 5. This row here tells you that lambda 2 times 1 is equal to minus 2, so lambda 2 is minus 2. And this row here tells you nothing at all, it's just row zeros. Hence, 5 times 1, 1, 2 minus 2 times 2, 1, 3 is equal to 1, 3, 4. And you can do just a quick sanity check to make sure that this is what you think it should be. 5 minus 4 is 1, 5 minus 2 is 3, 10 minus 6 is 4. So you're pretty confident that this is the correct linear combination. And by the way, this also shows that the vectors are linearly dependent. I think I marked this question last year, and some people just wrote this. They just wrote that, and of course that simultaneously answers parts A and B. So if you can just write that, great. But I don't expect you to be able to just imagine out the 5 and the negative 2. The mechanical way to do this is with row reduction. So. Okay, where's the
Okay, so we have a probability question here, and we have a child at the zoo, and they're going to be throwing a nut into one of 2 cages, and in those cages there's some red birds and grey birds, and we want to know sort of probabilities about, you know, what that are asked in the question. So probably the best way to tackle this is with a sort of a tree diagram, because the child first of all picks one of 2 cages with equal probability half for each, and then within those cages there's choices of red and grey birds. So let's just draw up a little diagram of what's going on here. So first thing that happens is the child picks a cage 1 or 2, and this happens with equal probability, so a half on each of these branches here. And so the child is randomly choosing a cage, then they're throwing a nut inside, and the nut can be picked up by either a red bird or a grey bird. And we're told that in cage 1 there are 3 red and 4 grey birds. I guess we have to assume that they are all equally hungry for the nut. So let's just assume that the probabilities for any of those birds is the same. So we've got the red bird and the grey bird. And in cage 1, there's 3 red and 4 grey, so there's 3 out of 7 times if it's equally likely that you'll get to a red bird, and 4 out of 7 for grey. So the probabilities are 3/7 that it'll be a red bird and 4/7 that it'll be a grey bird that picks up the nut. And in cage 2, there's 4 red and 2 grey. So 6 in total. I'm going to write it as 4/6 and 2/6. Of course you could simplify those fractions if you wish. Okay, so now we can answer the question, hopefully. So in part A, the child randomly chooses a cage and then throws the nut inside. What is the probability that a red bird catches and eats the nut? So if it happens this way, up into cage 1, there's a half probability of that happening, and then a half probability, a 3/7 probability that it's the red bird. So probability of a red bird comes from that, and it also comes from that. So it's just the sum of these two. So got a half times 3/7 plus a half times 4/6. Okay, so that's following that branch there or that branch there. And a little bit of arithmetic tells you this is 23/42. Okay, so for part B, we have a conditional probability because we're told that it's a red bird that picks up the nut, and we want to know what's the probability that it was cage 1 that the nut was thrown into. So here we want the probability of cage 1 given it's a red bird. Okay, so for this we need to know we need to know the probability that it's cage 1 and a red bird divided by the total probability that it's a red bird, which we worked out in part A. So this is hope I'm getting this right. Any complaints from internet land?
None yet.
So here the probability of cage 1 and red is like that. So we know what's the probability that we actually at this point here, we want to know what's that as a fraction of all the possible ways in which it could have been red, because we know it's red. And so that's that plus that. We worked that out in part A. So that's 23 over 42. And yeah, a little bit of fractions tells us that's 9 over 23. It's always a good idea when you work out these probabilities that you don't end up with numbers that are greater than 1. That's a dead giveaway, you've made a mistake. Yeah, anyway, I think these are probably reasonable.
Cool.
Okay.
So looks like we're going to go over time with the stream. I expect we'll be finished by 5. I just went down to the office and got us some sugar.
Oh yes.
So that we don't start making silly mistakes. So
More silly mistakes.
more silly mistakes, at least due to lack of sugar. The good thing about a 2-hour exam is you'll probably be alright. So
Yeah.
go for it.
Thank you.
So I think, yeah, perfect. Josh, do you want to say something about it? I'm just going to eat a biscuit.
This is nice. Yeah, nothing much to say about this. This is actually, this question sometimes has 3 parts. I've actually been a little bit tricky here and left one part out. Sometimes they make you calculate this number first, and then you put them all together. Here they're sort of making it a little bit different. Okay, so I have another probability question. So
Am I next or are you?
I think I am. It's one about nails.
Carry on.
So these are quite wordy questions. So you can see that we have a machine which is making nails, and we were hoping that it would make nails which were 20 millimeters long. But there's always a bit of error in production. So first things first, we need to come up with a distribution which would model the situation described. So here it says, let's assume that the nails are equally likely to be a little bit too long or a little bit too short. And what model would we use to model that? So first things first, it's always good to set up your notation. So I might start down here where it's dry. So let's let X be the number of nails over 20 mils in our sample of 12. So we're taking a sample of 12 nails and we want to have this number which is the number which are over a little bit too long. So the question is, what distribution will we use to model that? So we can model this as X is a binomial distribution, because we're really just doing repeated independent experiments, each with the same likelihood of success. And our parameters are n and p, where n is 12, number of experiments, and we're assuming that p, the chance of finding something a little bit too long, is 1/2. So we're assuming failure and success are the same. So this is our distribution. So part A, we can model it this way. Now, if you look at our sample here, so in the first line we have 5 too long, and in the second line we have 4 that are too long. So overall, 9 of these were too long. So we want to calculate a probability that says, how unlikely was it that I got a sample that looked like this? So for part B, I want, what is the probability that I could get something as extreme as this? The probability that my lengths would be greater than, sorry, the number of nails I got were greater than or equal to 9. So that's the situation I have up here. Now, this is 12 is a very small number, so I'm just going to use the binomial distribution itself to do this. And say that this is just the probability, well, x equals 9 plus the probability x equals 10 plus the probability x equals 11 and the probability x equals 12. So there's 4 numbers I need to calculate. That's not too bad. Because this is nice and p is a half, when you put it into the distribution, what you're going to have is everything will have a factor of 1 over 2 to the 12. So this is usually some combination of p and q, or p and 1 minus p, but here they're the same. So now what we have from the definition, so actually maybe I should just give you the definition up here. So the probability that x is equal to any number n is 12 choose n.
Use k.
K? Okay. Yeah, sorry, 12 choose k I already did. And then 1 over 12. Not 12, 1 over 2. To the 12, sorry. Oh no, it is actually, I guess this. 1 over 2 to the k. Then 1 over 2 to the 12 minus k. But those combine together into 1 over 12 to the k. Alright, so this is going to be 12 choose 9 plus 12 choose 10 plus 12 choose 11 plus 12 choose 12. Oops. And you can use a calculator. These are all just integers. If you do it either by hand or using a calculator, you'll find the first number is 220. The second number, so the second number is 12 choose 10, that's 12 times 11 over 12 times 11 over 2, so that's 60. No, sorry, 11 times 6, so 66. 12 choose 11 is actually just 12, and 12 choose 12 is 1. And that's all times 1 over 2 to the 12. So if we sum those up, and I'm just going to look at my earlier working, this is 299 over 4096. I think that's right, is that a power of 2? And when you calculate that, that's approximately 0.07. Oh, I do need to calculate that. So 299 divided by 409672. Approximately that. So that's about 7.2%. So that's how unlikely it was to find something this extreme, 7.2%. Now, the standard of evidence I think we take for this course is 5%, is that right? So this is not unlikely enough that I'm convinced there's something wrong with my machine. So, well, since 7.2% is greater than 5%, which is my sort of threshold for thinking something suspicious, it's not too unlikely. It's not sufficient evidence of a bias in length. So we typically take 5%. You may want to, if this is actually a real practical example, you may want to have a different, more fine number, but here, 5% is our threshold. Any comments? I might just make a quick comment, because some people may be tempted to try and approximate this binomial with a normal, which is a nice thing to do for very large binomial distributions. I did attempt this before I came here, and I got 20% as my answer, so the numbers are quite different. So if you use the normal, you could easily go from a situation where you were suspicious to where you just weren't suspicious at all. Here it didn't actually make a difference, but 7.2 and 20, they're quite different.
Yeah, I remember marking this question actually, and a bunch of people did unfortunately use the normal distribution to make this approximation, and they did a great job. But the question wasn't about that. Yeah.
Yeah, four numbers is not enough for me to sort of shirk the calculation.
Yeah. I mean, yeah, look, you can do it here. I mean, that's... Yeah. You'll be asked to do the normal approximation, or it should be clear to you where, you know, the n value is like 200 or something like that. Cool.
Here's a new question.
Yep, thank you. So my question has some maple output in it. What have we got first? The A and then the B part. Can we get the B part up as well?
I might just make this visible. This is the entire
cool.
thing.
All right, let's do that. Yeah, we need the whole question for this one. Cool, thank you. So the point here is that you have this maple output and you have to interpret the maple output. And the key is that since A times B, the matrix multiplication, well, maybe I'll get some notation first. Let B1, B2, B3, and B4 be the matrix B. Then A dot B, this matrix multiplication, is equal to A B1. This is the first column of this product. A B2, A B3, A B4. And we get given this product is 0 B1, 4 B2, this is what the maple output's telling you, negative 3 B3, and 3 B4. And so it's kind of telling you what the eigenvalues and eigenvectors are. Hence, this one is equal to this one. A B1 is 0 B1. A B2 is equal to 4 B2. A B3 is equal to minus 3 B3. And A B4 is 3 B4. So it tells you what all of the eigenvalues and eigenvectors are. In particular, I think this is the one the question is asking for. Is that right?
Yep.
Hence, B2 is the eigenvalue 4. The second part of the question is to find a basis for the kernel, and this is a little bit tricky. You see here we have that B1 is in the kernel because A times B1 is equal to 0 B1, which is equal to the 0 vector. So here you have B1 in the kernel, but is that all of the kernel? How interesting. So for part B, since B1 is in the kernel of A, that means nullity of A is at least 1. There could be other stuff in the kernel we don't know yet. We don't know. Let's look at, yes, sorry. Thank you, yes. Awesome. Since B1 is in the kernel, yes, good. Is that everything? Let's see. Let's talk about the rank. Well, maybe I'll mention some property of, before I tell you about the rank, I'm going to mention a property of eigenvalues. All eigenvalues all the eigenvalues are linearly independent. And all these eigenvalues are in the image of the matrix A.
Eigenvectors.
Thank you. This is why I need sugar. So maybe I'll be explicit here. Since the eigenvectors B2, B3, and B4 are both lin this is a property of eigenvectors. All eigenvectors from distinct eigenvalues are linearly independent, and in the image of A, then you've got the image of A containing at least 3 linearly independent vectors. So the rank of A being equal to is at least, what did I write here? Is the number of columns is at least 3. At least 3 of the at least the dimension of the rank of A is at least 3. Hence, nullity of A by the rank nullity theorem being 4 minus the rank A is equal to is less than or equal to 4 minus 3 is equal to 1, and the nullity of A is therefore exactly 1. You know it's at least 1 because it's got this in it, and now we know it's bound above by 1. So kernel A is the span B1. When marking this, I didn't see anyone who got this right last year. This is one of the harder questions from the exam.
Definitely a hard question. Testing if you really know what's going on.
Yeah.
Yeah.
Cool. Any comments?
I think it's fine. Yeah.
Okay.
Yeah. This
Cool.
was the hard thing to spot and interpret what this all means.
Yes.
Yeah.
Cool. All right.
On to question 4 now.
Yeah.
Isn't it? Yep.
And a question like this is really why you have numbers at the top of your exam, because you could spend half an hour just on that question, trying to figure out that question. Do not spend half an hour on that question.
Cut your losses.
Yeah. Just if you be brutal when you reach that number at the top of the exam, move on. It's over.
Okay, so question 4, we have a reduction formula question, and it tells you a reduction formula, and it's very important when you read these questions or questions like them to just carefully read and ask what's actually being, think about what's actually being asked here. You're not asked to prove this reduction formula. Okay, so it's very easy to see, reduction formula, go ahead and try and prove it, and then 10 minutes later you realise, I didn't have to prove it, didn't ask for that. So we're not being asked. It says you are given this reduction formula. Okay. All right. So we just have to calculate an integral that is given there, and hopefully it's got something to do with the reduction formula. And in fact, well, it's pretty obvious that integral we've got there is the same integral in the reduction formula where the n is now 2. So this is I2. Okay. And the reduction formula tells us what to do with I2, and notice this reduction formula is valid for n that's greater than or equal to 1. So it's definitely valid for a 2 here. It's even valid when that was a 1. So let's just use that now. Okay, so we have, according to the reduction formula, this is the reduction formula with n equals 2. This is 2 root 2 over 1 plus 2 times 2. There was some n's in this reduction formula, wasn't there? There was the n that's the n there, the 2, minus 2 times 2. That second 2 is the n over 1 plus 2 times 2 times I1. Okay, now this is only progress if it's going to be easier to calculate I1 than I2. Okay, so this is 2 root 2 over 5, and this is 4 over 5 times I1. And for I1 we can use the reduction formula again. And the reduction formula tells us that this should be 2 root 2 over 1 plus 2 times 1 this time. Now we've got n equals 1. Minus 2 times 1 over 1 plus 2 times 1 times I0. Okay. Alright, hopefully this is going to be some help to us. We just need to do a little bit of simplification here. So we've got some things involving root 2's here and here. I think that's minus, so that's 6 minus 8. It's minus 2 lots of 2 root 2 on 15, I think. So this has got a 3 on the bottom. 5 times 3 is 15. Have I made a mistake?
I'll tell you in a second.
You're going to make me square and wait till the end. Is it wrong or is it...
No, I mean, I'm still calculating.
Okay. Okay, so minus that's 3, 8 over 15, I0. Okay. Now, can we use I0? Can we use the reduction formula again for I0? No, because it's only valid for I greater than or equal to 1, so we need to calculate this one directly, and hopefully this is going to be easy. So that's what I0 is, and in fact, yes, we can just immediately write down a primitive for that. That's just going to be 2 times the square root of 1 plus x. How did I put these around the wrong way? 0 to 1. And so that's putting in 1 is 2 root 2 minus putting in 0 minus 2. Okay, so basically just got everything we need now. Just put this number into there and simplify. So the integral we want, which is integral from 0 to 1 of x squared over the square root of 1 plus x dx is equal to minus 2 root 2 over 15 minus 8 over 15 times by 2 root 2 minus 2. And you'd probably, I think you get the marks for that, but it's polite to simplify if you've got enough time. But if you don't have enough time, it's better not to. Yep. Okay, so I think that's it's either the right answer or very close to the right answer. Anyone complaining?
No one's complaining. I wanted to say that I prefer to build these up starting with I0 and then construct I1 and then construct I2 because there's just less brackets that way.
Yeah.
I am concerned because minus 2 and that minus 16.
So that should be plus. 8 minus 8 times minus 2, should it be plus?
Yes, and there should be a minus sign here, I think. Or minus 16, but then minus 16 minus 2 is minus 18.
Okay, okay,
yeah. So, maybe it's...
Yeah, I should have checked it with Maple, shouldn't I? Can't do that in the exam though. Alright, anyway. Move on. 18? Quick cricket.
Pretty sure that's an 18, minus 18.
Minus 16 minus 2 is minus 18, yeah. Okay.
I won't comment on the fact that it seems like it's the wrong sign, but okay.
It's a positive number. What's gone wrong?
Yeah, that was a negative number you wrote down.
Alright, I'm gonna do that. I'm gonna do that one and we'll figure out.
Alright, so let's
My answer was it was different to my answer I got here, so yeah.
Alright.
And who's up next? Is that me?
I think so, yes.
Cool. Black pen. Okay, so you have some, again, a Maple session, you have some function, you have the Taylor coefficients. Using the Maple output or otherwise, that means use the Maple output. Write down the values of the first derivative at 0 and the third derivative at 0. So I might remind you that since f of x, is going to be approximated by f0. I'll just say x to the power 0. These brackets here, by these brackets here, I mean the 0th derivative, which is just the function value itself. The first derivative evaluated at 0 on 1 factorial x to the 1 plus squared plus this stuff is equal to 0 plus 2x plus, that's 0 plus 2/3 x cubed plus other stuff by my Taylor. Is my other stuff, is that on the screen? Yeah, it is.
Yes.
Sweet. So using my knowledge of the Taylor approximation and the Maple output, I can figure out that what the derivatives are. By comparing the coefficients of x, I know that f1 evaluated at 0 on 1 factorial is equal to 2, which means that f, the first derivative evaluated at 0 is just 2. And by comparing coefficients of x cubed, I know that the third derivative evaluated at 0 over 3 factorial is equal to 2/3, which tells me, I'm just going to read out my answer, that the third derivative evaluated at 0 is 4. Yeah. Good. The next part of the question is to, so that was part A. Part B asks you to find a rational approximation to the natural log of 3. Well, first of all, you need to know what x value to use. What we've got here is f of x being equal to natural log of 1 plus x over 1 minus x. And it would be handy if that was equal to the natural log of 3. And so we have to unravel this to figure out what x value will give me a 3 here. So if 1 plus x on 1 minus x is to be equal to 3, then, well, I could just solve this. 1 plus x is equal to 3, 1 minus x, which gives me 4x is equal to 2, so x is equal to 1/2. Great. So if I plug f of 1/2 in, that should be equal to ln of 3. And f of 1/2, well, I just throw it into my Taylor approximation. There's going to be 2 times 1/2 plus 2/3 times 1/2 cubed, plus, using my other Taylor coefficients, 2/5 times 1/2 to the 5, and I won't bother with the other ones. And this gives you 1.09583 recurring, which is a rational number. And by the way, it's pretty close to actual. So by the way, ln3 is 1.09686. So this is actually pretty close to this. I get 1.1095, and here's a more accurate approximation is 1.0986. So it's pretty good up to 3 decimal places. 2 decimal places.
Okay, I might just jump in and say I checked my my calculations with Maple. All right. I had it right in my notes. I2. Sorry. I2 is just for the record minus 16 on 15 plus 14 on 15 root 2. That's a positive number, isn't it? Yeah.
Mm-hmm.
Yep. Okay.
She rubbed it out quicker than I had a chance to make a comment. Because this question that Danny was working on, it did say use the first 2 terms.
Oh, use the first 2 terms. Okay.
It's still a rational approximation. So.
Yeah, but I used the first 3 terms, so.
Well, he used the first two and something.
Yeah.
Oh,
You
so I
actually-
did.
You did actually use the
I
first
did.
two.
Okay. Yeah, the question should have said use only the first two terms. So, all right, that was more than what was intended.
Right, I'm up. So we have to solve an ordinary differential equation, an ODE. Now, it doesn't look pretty like most of the ones we tend to encounter, but it's not so bad, because if you do look at it, it is actually just linear. So it is a linear first order ordinary differential equation, and we know a good technique for attacking those. That's to use the integrating factor. So just to remind you, this is of the form dy dx plus px y equal to q of x. And I probably would write this in the test because I tend to make mistakes about what p and q are, where p of x is equal to the function minus x over 1 minus x squared. Now, I tend to trip up with this minus sign here. That's why I want to make sure I explicitly pulled it out. It's plus p, where p is this. And q of x is just 2 over 1 minus x squared. Okay, so to answer this question, we're going to use the technique of integrating factors. So let's just get the integrating factor. Integrating, and maybe I'm actually a little bit upset with myself. An integrating factor is the exponential of the integral of p of x, which is the e to the integral of p, which is minus x on 1 minus x squared dx. I'm happy to see this minus x on top because it's pretty much the derivative on the bottom. So by inspection, I can write this as e log 1 minus x squared. I guess I should have absolute values, but I'm going to ignore that. This doesn't quite work as the integral.
Actually, you don't need it absolute values because you've said an integrating factor.
Oh, I see. Well, it also says that x is between 0 and 1, so this is a positive thing. This doesn't quite work. If I take the derivative, I do get a 1 over 1 minus x squared, but I also get a minus 2x. I don't want a minus 2x, I just want a 2x. So let's fix it up by putting a half in, and I don't need a plus c. That's why I said an. It's just an integrating factor, this one. Now, logs are lovely. They actually are. So I can write this as e to the log of the square root. So I'm bringing this half up as a power. 1 minus x squared. And e to the log of something is quite lovely. It's the square root. So that's my integrating factor. The e's and the logs actually vanished. I just get this nice square root. All right. Now, negative. Well, there's a minus sign coming out here, right? The derivative of this is
Sorry, carry on. Yep.
Yep.
Thank you.
Cool. Right. So multiplying. So this is the lovely thing about the integrating factor, and you should remember this, is multiplying by the integrating factor. So the one I'm found. Gives, and I always go straight for the conclusion. I don't actually do the multiplication on the left-hand side. I just say, well, the whole point is it becomes the derivative of y of x times the integrating factor times the square root of 1 minus x squared. So the left-hand side is really lovely. It's just a derivative. The right-hand side, not so much. Becomes 2 over 1 minus x squared times the square root of 1 minus x squared. And that is 2 over root 1 minus x squared. Now this left-hand side I can easily integrate, but this right-hand side I can also easily integrate. But I can only easily integrate it because I remember I'm provided with a table of integrals. And if I look in this table, I find that this here is the integral of sine inverse x. There's a factor of 2 I'll need to take care of. So, need more space. So we can integrate both sides, one easily and one using the table. Integrating gives, well, integrating a derivative is lovely, it's just y of x square root 1 minus x squared. So you get this side, when I look on the table, I see it is actually just 2 times the sine inverse of x, and of course there is a plus c, as there always is. Alright, so that's the general solution, but we actually have a condition here. We have that the value of the function at 0 is equal to 1. So using y equals 1 at x equals 0, we'll pin down this constant. It gives me that, well, this becomes 1 times 1, the 2 times the sine inverse of 0, c, and sine inverse of 0 is actually just 0. Therefore, c equals 1. And it's quite a nice equation, so I think it is polite to write the final solution down in a nice form. So hence, y of x, well, it'll be equal to 2 sine inverse of x plus 1 over the square root 1 plus x squared. And I think that answers the question. Any comments?
No, I think it's just straightforward. Yep.
Yep. Oops.
Okay, so the next one is, I guess it involves a chain rule. So, okay, so we're given some information about a function t of 2 variables x and y, and each of x and y depend on another t, little t. The first one was a big T. So maybe I'll just write t is, I guess it's in the question, isn't it? Okay, so we've got that, and I'll just extract this information. X is t cubed, and y is t squared. I think I have that right. Okay, so we want to use the chain rule to calculate the rate of change of temperature along a path dt by dt. So what we're doing here is x and y are changing as little t changes, and we want to know how big t changes as a result. So we need the chain rule. So this is, the chain rule says, well, t depends on x and y, and each of those depend on little t. So there's 2 ways in which capital T depends on little t, one via x and one via y. I'm just going to write down that. We have 2 terms, dx by dt. This is a partial derivative because t depends on x and y, and then times dx by dt. And t also has some dependence on, capital T also has some dependence on little t via its via y, so there's a dt by dy by dt. Okay, so we've got to calculate these derivatives. You could calculate those separately first if you want. I'm just going to write them in now straight away. So capital T, the partial derivative with respect to little t is that's 8x minus 4y. That's this part. And then dx by dt, well, x is t cubed, this is 3t squared. And then the next term, capital T with respect to y, the partial derivative. So that's differentiating this with respect to y, holding x constant. We've got minus 4x plus 2y. And then dy by dt, y is t squared, so that's 2t. Now the question asks for this as a function of t, so we'd better convert these x's and y's into t's here. Okay. All right, so that's 8 8x, so this is 8t cubed minus 4y, y is t squared, 3t squared, minus 4t cubed, plus 2t squared 2t, and then we want to just collect all that up together, and it's 24t to the 5 minus 20t to the 4 plus 4t cubed. Okay, now a common question is whether or not you could have just substituted these into here and differentiate with respect to t, and of course you could and you'd get the same answer. The question did say to use the chain rule, so it really is asking you to do this. I suppose you would be possibly using the chain rule. Not really, no, you wouldn't. If you substituted those into there, you just get a polynomial in t. There's really no chain rule involved. So I think you have to do it this way to get the marks. You need to know the chain rule, you know, for other reasons. Okay, so that's A. B, what was B? B says we want to, oops, I've lost my question. Find the rate of change of temperature when the ant is at 0.84. So we need to know how to find the 0.84. 0.84, well, if x is t cubed and y is t squared, maybe I'll just write that in there. This is telling us that t is 2. So we want to know what this is when t equals 2, essentially. So let's just say at that point, this works out to, well, I'll just plug in 2. 24 times 32 minus 20 times 16 plus 4 times 8. This is, I cooked this one earlier. It's 480. And then in part C, we're asked about how far the ant travels in a certain time. So it's going, sorry, how far it goes from 0.00 to 84. Now it's travelling along a sort of curved path from 0, 0, which is where t equals 0. That's pretty easy to check as well. Up to 0.84, where t equals 2. And so this is an arc length question. We need to calculate a distance, an arc length, which is the distance. So the distance here is the integral. The variable t is running from 0 to 2. I worked that one out in my head. It's on my diagram, so it's clear where that came from. Square root dx dt squared plus dy dt squared. You need to know the arc length formula, of course, for this. It wasn't in the question. And so let's just work this all out. This is easy to work out. That's just 3t squared. And 3t squared, 3t squared squared is 9t to the 4th. I'm just going to go straight to that. Y is t squared, so the derivative is 2t, and square that, that's 4t squared. And hopefully we can do this integral. I'm not off the bottom of the page yet. I'll just take a t squared out. And I'm being very careful here, because when you take this outside the square root of t squared, it becomes the absolute value of t, which happens to also be t, because we're in the range from 0 to 2. I'll just make a note of mod t equals t for t in 0 to 2. And shall I go down on the next line? Yeah, I think I can squeeze it in. So this is, I can just do this integral. Actually, I'll tell you what, I'm going to go over the other side over here. I think that's better. Better for all concerned. So this is just doing this integral. That's, if I integrate something to the half, I'm going to get 2/3 of that thing to the power 3 on 2. And if I differentiate this, I'll check that, oops, I'll pop out another 18, so I'll put a 1 over 18. And then we just have to evaluate this. So this is, that's 1 over 27, outside of 40. That comes from t equals 2 in here. That's 4. 9 times 4 plus 4 is 40 to the power 3 halves, minus putting in t equals 0, 4 to the 3 over 2. That's probably a good enough answer. You can just take out a factor of what is it, 8. This 4 square rooted cubed is 8. But that's probably not really necessary. So this is the length. Is this a positive number? Yeah, I think it is. Yeah, this it's bigger than 10.
Yeah.
So it's a positive number. That's a good thing. Yeah, it was walking a positive distance along here. Yeah, cool.
I like that Jonathan does a sanity check on this, because you just want something quick and easy you can do to let yourself know that, hey, is there any alarm about this? Is there anything obviously wrong? And if there is, you'll just need to come back to it later. Cool. Last question. Good. A tank initially contains 1,000 litres of pure water. Whenever you have one of these questions, it's a nice idea, at least I find it a nice idea, to draw a picture of what's going on here. You have a tank, get out your blue pen, and you fill it with 1,000 litres of pure water. Let's see, salt water begins pouring into the tank and stirring, and so here we have some kind of inflow. Don't yet know how much stuff is going in, but we'll get there. And the second pipe drains the water out again, and there's some kind of outflow. The rate of mixture is always okay, here we go. So the amount of mixture coming in is equal to the amount going out, so it's always 1,000 litres in the tank. Salt water coming into the tank has 2 grams of salt per litre. It tells me about the kind of density of salt here, but I don't know how many litres are going in. And it tells me that there are k litres per minute flowing in. So at k, which tells me that the outflow here, so this is 2 grams of salt per litre, and there's k litres per minute, and I know that there are going to be k of salty brine going out of the tank. So, part A. You should always let x be the amount of salt in the tank, or the amount of stuff that you're measuring in the tank. It actually tells you to let x of t be amount It actually tells you that, but if it didn't tell you that, you should write it anyway, because that's a great thing to put down there. Now we need to come up with the differential equation which describes the amount of salt in the tank at time t. It actually gives you the equation there and then asks you to justify it, but you could, in theory, come up with this equation yourself. So x prime of t is always equal to the inflow of salt minus the outflow of salt. The inflow is kind of easy. It's 2 grams of salt per litre, and there's k litres going in, so it's 2k. The outflow is a bit more sophisticated, because currently there are x grams of salt in the tank, and you're going to take out k litres and just kind of, that x has to be distributed evenly amongst the amongst whatever stuff you have. So it's going to be however much you have per litre, which is x divided by 1,000. Maybe we'll call x of t divided by 1,000, and you're going to remove k litres where each litre has this density of salt in it per litre. And I can write that out according to the formula. If I take a common factor of k on 1,000 out, then I get left with 2,000 minus x of t. Yeah, which is what I've got. And the initial condition say x of 0 is equal to 0 because of the tank is initially full of pure water. Good. But even if you're unable to extract that information from the question, you've got it there as part A, so you can still do part B.
Can I interrupt for a second?
Yeah.
I would be happier if there was on paper an explanation for what this term was.
Oh,
I know you said verbally this is the density of the salt.
Okay.
So, but I feel like if you say it verbally during the exam, well, one, no talking during the exam. So I'm not going to know what you said. You'll have to actually write that down, what this means.
Okay. I'll do that just to exemplify good behavior. Oh, sorry. Yeah. This is the amount of salt you would expect there to be per 1 litre in the tank. Right, B. Solve this differential equation. Well, it's a first order linear equation, so we should know how to solve this stuff. X prime of t, can I write it out as plus k on 1000, x of t is equal to 2k. Just taking this equation and rearranging it so it's a nice linear thing. And then I'll use my integrating factor. Since it's first order linear, I can just get an integrating factor out of this. E to the integral k on 1000, sorry, dt is equal to the e to the maybe I'll say it's kt on 1000. So this equation becomes times x t is equal to 2k e to the kt on 1000. And now I can integrate both sides and I get e to the kt on 1000. X of t is equal to the integral of this, which is 2000 e to the kt on 1000 plus c. And I can use my initial condition at this point. When t is equal to 0, x of t is equal x of 0 is equal to 0. So I can get 0 here, 0 is equal to 2000 plus c, which means that c is equal to negative 2000. And finally, I can say that x of t is equal to 2000 1 minus e to the negative kt on 1000. Cool. So there's my answer to part B. And just as a kind of quick sanity check, when x is equal to 0, this is 2000 times 1 minus 1, which is 0. So that's good. So there's my answer to part B. Part C. If there's 1 kilogram of salt in the tank after 5 hours, find K. Okay, so if x of 5 is equal to 1 kilogram of salt. 1 kilo of salt in the tank after 5 hours. So not 5. Remember, x is grams of salt. measured in X is measured in grams, so kilograms, that's equal to 1,000. Aha! If X of 5 is equal to 1,000, then
It's 5 hours. Was it at our time?
is that 5 in minutes? Salt per K liters per minute. 5 times 60. Right. 5 times 60. What is that?
300.
300. Thank you. Oh, all the units were messed up in that one. I fell for it. I thought I had it here, but then that was minutes instead of hours instead of minutes. Okay, good. Then what do we get here? Well, this is 2,000 1 minus e to the negative k times 300 over 1,000 is supposed to be equal to 1,000, and fortunately a lot of this stuff goes away. That can cancel with most of that. I'll just write it as 1 minus e to the negative 3 on 10k is equal to 2.
A half.
Half, thank you. Good, that makes more sense. And then 1/2 is equal to e to the negative 3 on 10k. Now I need my calculator. Sorry, I might get that in a moment. Negative 3 on 10k is equal to ln 1/2, so k is equal to 10 on 3, negative 10 on 3 ln of 2. Thank you. 10 divided by 3 times natural log 2. Approximately 2.3.
Well, this is probably a reasonable answer anyway.
That's probably a reasonable answer anyway,
Yeah.
yes. And finally D, what happens as t goes to infinity, or what happens to x as t goes to infinity? Well, the limit as t goes to infinity, x of t is equal to t goes to infinity of 2,000 and since k is positive, this thing will equal to 2,000. So k being not a negative number gives us that this thing will go to 0 as k gets very large, and so the whole thing just goes to 2,000. Sorry, was that? It should have been a 2, shouldn't it? No, sorry, that's fine. It's 1,000. It's 1,000, and this kind of makes sense because it's 1,000 liters of water, and in the long term, it'll all be of this kind of density. So you would expect that if you keep putting in 2 grams of salt per liter, then the whole tank will eventually fill with 2 grams of salt per liter, and the amount of salt you'll have in your 1,000 liter tank is 2,000 grams. So, good. Sanity check made me feel happy about that answer. I think I'm done.
Yeah. you look pretty tired.
Yeah, thank you.
Yeah.
The
Okay.
biscuits only went so far.
Yeah. So I think that's it. Yep.
All right.
We're done.
Cool.
So
Yep. So, well, good luck with your final exam. Don't forget there are still consultation hours. For
the
this
drop-in
week and next
centre
week.
will
Yeah,
be
the drop-in centre's
open next week. Yep.
Yeah, and Maths
and
Soc-
the Ed Forum.
Yes.
The Ed Forum's a good place to post questions, and Maths Soc's having some
event which is we've kind of stepped on the toes
Yeah.
off, but you know, there we are. Cool. All right. So thanks for watching, and good luck in your exam.